So part of why the previous video was so short is because I'm anticipating this video to go quite a bit longer than our usual videos do. This is all one chapter and it's just a really big one. And it's on the levi-malcev theorem. I believe that is how you pronounce it. And we start out with just a bit of a discussion. We're going to let E be a complete normed vector space over the reals. It's over the reals and not is the reals. And it's going to have a continuous endomorphism, which we're going to call U. We have seen that the sequence u to the n over n factorial, basically the nth term of the Taylor series of the exponential function. This sequence is summable as the linear functions over E, with e to the u being equal to being also written as just the exponential function of u as the sum from 0 to infinity of u to the n over n factorial. Now we're going to let E be a vector space over the field K with a nilpotent endomorphism U. Then our series of u to the n over n factorial 0 to infinity has finite non-zero terms and we can define the exponential of u, the natural exponent exp u, as above. With these definitions agreeing when K is equal to the reals and E is complete and normed. If V is a nilpotent endomorphism of E, that commutes with U, then we get that e to the u times e to the v is equal to, of course we can just directly substitute in their definitions first off. We basically have to, as sums and then we can sum over both just multiply them component-wise. I mixed up my variables. Over n factorial p factorial, which is equal to the sum. This is over n and p in the way you'd expect. This is from q equals 0 to infinity of 1 over q factorial times the sum where n plus p equals q, and I'm guessing they're going to be non-negative, of q choose n. Well, I guess that will account for any negative terms there. Of u to the n times v to the p, which is, there's some more combinatorics here. Q equals 0 to the infinity, 1 over q prime, and then this term inside simplifies to be u plus v to the q, which is just the definition for the exponential of u plus v. As e to the u times e to the negative u equals e to the negative u e to the u equals e to 0, there's 1. We see that e to the u is an automorphism of e, because it always has a two-sided inverse of e to the negative u. If further, e is an algebra, not necessarily associative, and u is a nilpotent derivation of e, then EU is an automorphism of E as an algebra. As for x and y in E, we have u to the p of x, y is equal to the sum of r plus s equals p of p choose r, u to the r times x, u to the s times y. For non-negative integer p. Thus we have that e to the u of x times y is equal to the sum of non-negative integer p, 1 over p factorial times u to the p of x times y, which is equal to the sum of p greater than or equals 0, the sum of r plus s equals p. So this first one is the definition of e to the u, the second one is the u to the p, so this gives us, of course, u to the r x over r factorial times u to the s of y over s factorial, which is equal to the sum of r and s, both from 0 to infinity, of, that's just changing the summations, The actual term inside is unchanged. And so this just gives us e to the u of x times e to the u of y. Now we're going to let G be a Lie algebra. If x is in the nilpotent radical of G, then the derivation given by the adjoint, so G adjoint of x, is nilpotent as a derivation of G. Thus, we can define, and now we have a definition that a special automorphism of G is an automorphism of G of the form e to the, it's the exponential map of the adjoint of x, where x is in the nilpotent radical of G. And we see that this leaves every ideal. These special automorphisms leave every ideal of G stable. I'll come up with another definition here. We're going to let G be a Lie algebra with a radical R. A Levi subalgebra of G is a subalgebra of G supplementary to R. We note that Levi subalgebras are isomorphic to G over its radical, and so are semi-simple. As a semi-simple algebra has only 0 in common with R, every semi-simple subalgebra H such that G equals R plus H is a Levi subalgebra. I don't know if it's Levi or Levi. So the image of a Levi subalgebra under surjective homomorphism is a Levi subalgebra. And that brings us to the theorem in question. So we have our theorem, which is of course going to be the levi-malcev, a Lie algebra G must have a Levi subalgebra S. And every Levi subalgebra of G is the image of S under a special automorphism, which is just some e to the power of the adjoint of x for nilpotent x, as we saw. So proof is going to be pretty long, I think, fairly long. Let R be the radical of S, G, not S. We first handle two special cases. Case A is where the bracket of G and its radical is just the element 0. Then we get that by our previous proposition. G is the product of its radical by its derived algebra. Where dg is semi-simple. Thus, dg is a Levi subalgebra. If S prime is a semi-simple subalgebra, then S prime is its own derived subalgebra from previous theorem. So S prime is contained within the derived subalgebra of derived algebra of G. With the derived algebra of G being the unique Levi subalgebra of G. And the other special case is where the bracket of G and its radical is non-zero. And the only ideals of G inside of R are 0 and R. We see that then the bracket of G and R has to be R. The bracket of R and R has to be 0. And the center of G has to be 0. Let M, respectively, N be the subspace of the linear functions of G of linear mappings of G into R whose restriction to R is a homothety, or in the case of N, just 0. We see N is of codimension 1 in M, for little m in big M, let theta m be the ratio of the homothety of R by M. I'm also going to let sigma be the representation of G on the linear maps of G canonically derived from the adjoint with sigma of some x acting on U by the G adjoint of x bracketed with U for all x in G, U in the linear maps on G. Some House of Leaves stuff going on in the book here. This is scary. So clearly, sigma x acting on M is within N for all x in G. So if x is in the radical, y is something in G, U is in M, so use a linear map of G into R whose restriction to R is homothety. Then sigma of x acting on U of y is the bracket of x on U of y minus u of the bracket of x and y, just by that definition up above, which is equal then to negative of the ratio of the homothency of u multiplied by the bracket of x on y. Since that's because x and u of y are both in the radical, and we have that the radical bracket with itself is 0. So this all simplifies down to sigma of x acting on u is equal to the negative of the adjoint of lambda u acting on x. And we're going to note that the linear maps of G contains M contains N, and N contains P, which we are going to define here next. Like I said, they kind of wrote this out like House of Leaves, so it's hard to exactly know what order we're supposed to read things in, but as the center of G is 0, the mapping of x to the G adjoint of x defines a bijection theta of R onto a subspace. This is our P from above. This is a subspace of LG. And we're going to see that it's within N. This is stable under sigma of G and contained in N, as you see above. N, since the radical is a commutative ideal, and the above equation, that's where we calculated that the sigma of x on u is the negative of the adjoint of the ratio to the homothency of u on x. And that equation shows that sigma of x on M is going to be with things inside of P for x in R. The representation of G on M over P, which we're going to write as V, derived from sigma is thus 0 on R and defines a representation sigma prime of the semi-simple algebra G over R on V. For all y in this G over R, the space of V under sigma prime of y is contained within N mod P, which is of codimension 1 in V. Thus, there exists U0 in M such that it has a homothency ratio of -1, 1, and sigma x on UO is in P for all x in G. The mapping from x to the inverse of phi of sigma x on U0 is then a linear map of G into R. Use restriction on R is the identity. And so its kernel is a subspace S of G supplementary to R in G. As S is the x in G such that sigma x upon this UO is 0. S is a subalgebra of G, and therefore a Levi subalgebra of G. We're almost through case 2 for a, depending on your definition of almost. Now we're going to let S prime be another. I guess we should do this as another paragraph, right? We're going to let S prime be another Levi subalgebra. Then for all x in S prime, let h of x be the unique element of R such that x plus h of x is in S. Since S is a subalgebra, and R is commutative, then for x and y in S prime, we have that the bracket of x plus hx with the y plus hy is equal to the bracket of x and y plus the bracket of x and h of y plus the bracket of h of x plus y, and y, not plus y. That doesn't make any sense. It's going to be inside S. Hence, h of the bracket of x and y is the adjoint of x on h of y minus the adjoint of y on h of x. Then there exists element a in the radical such that h of x is equal to the negative adjoint of x on a, or alternatively the adjoint of a on x, for all x in S prime. And then we get that x plus h of x is equal to x plus, h of x is just the bracket of a on x, which is, we can write this function of x as 1 plus the adjoint of a on x. As R is commutative, the square of the adjoint of A is just going to be 0. Hence, e to the adjoint of A is just this 1 plus the adjoint of A we have above. As R is invariant under the bracket of G, that's not actually true. It's R is equal to the bracket of element of G and an element of R. We have then that this e to the adjoint of A is a special automorphism of G. And we have that as mapping S prime into S. That is case 2 then. Case C is the general case. So let me just check real quick something. How long has it been? How long have we been? It's been 40 minutes and we're like halfway through. That's good. I mean, this is all one chapter, so we kind of just got to power through if we want it to be all continuous. We're going to argue by induction on n equals the dimension of the radical with everything being trivial if n is just 0. So let the theorem hold for Lie algebras with radical of dimension less than n. By case A, we can assume that the bracket of G on R is non-zero, because otherwise A just solves it instantly. As we know that the bracket of G and R is nilpotent, it has non-zero center C. So we're going to let M be a minimal non-zero ideal of G contained in C. And now, by case B, we can assume that this M is not R, because otherwise it is solved automatically by case B. Let F be the canonical mapping where F goes from G onto G prime, which is a quotient of G by this minimal non-zero ideal of G inside the center. Then the radical of G prime is R prime, which is R over M. By our induction hypothesis, G prime has Levy subalgebra H prime, then letting H be the F inverse of H prime is a subalgebra of G containing M such that H prime is equal to H over M is semi-simple and so has H has a radical M. Once again, by the induction hypothesis, H is equal to M plus S for some semi-simple subalgebra S. Thus, by the fact that G prime equals R prime plus H prime, we have that G, as we saw, is G is R plus H is equal to R plus M plus S, which is equal then to R plus S. And so S is a Levy subalgebra of G. Let S prime be another Levy subalgebra of G. Then f of S and f of S prime are Levy subalgebras of G prime. So by the induction hypothesis, there exists an A prime inside of the bracket of G prime and R prime such that e to the adjoint of A prime of the image under f of S prime is just f of S. If we have A in the bracket of pick A in the bracket of G and R such that f of A is A prime, then S1 is e to the adjoint A of S prime inside of M plus S, which is H. Then S1 and S are Levy subalgebras of H, and by the induction hypothesis, there exists B and M such that e to the adjoint of B on S1 is S. Hence, I'm just going to go to a new line. S is e to the adjoint of B on e to the adjoint of A on S prime. And finally, as M is in the center of G bracket R, we can use the multiplicative rule on these exponentials and get e adjoint of B plus A for B plus A being in G and R. Really should be and, not for, but whatever. And that is our I forget what it's called. Special automorphism, is it called? I should verify that. That is, yeah, that's our special automorphism. Alright, so we're almost done here. We got one more section of this chapter, which consists of 4 corollaries. As you do, we need to know the consequences of this on our thinkings. So let's look at those. Corollary 1. Let S be a Levy subalgebra of G and H, a semi-simple subalgebra of G. Well, it comes in two parts. There exists a special automorphism of G mapping H onto a subalgebra of G, of S, not G. And B, H is contained in a Levy subalgebra of G. And our proof. Let R be the radical of G. We're going to let A be equal to sum of H and R be a subalgebra of G. Then A over R is semi-simple, and R is solvable. So R is the radical of A, and H is a Levy subalgebra of A. We also have that H prime being defined to be the intersection of A and S is a supplementary subalgebra to R in A, and hence is a Levy subalgebra of A. Then there exists an element A hat in A and R such that E times the adjoint in A of A hat, they don't even call this A hat in the book, so it's like the A adjoint of A, and it's just like a mess to read. And this maps H onto H prime. Now, A hat is a member of the bracket of G and R. E to the A adjoint of A hat maps H onto a subalgebra of S, and E to the negative adjoint in G of A hat, acting on all of S, is this is a Levy subalgebra of G containing H. And there's another second corollary is an immediate consequence of the first corollary. A subalgebra H of G is a Levi subalgebra if and only if H is maximal and semi-simple as a subalgebra. And that follows immediately from above. So we can jump right into corollary 3, which states if we let G be a Lie algebra with an ideal M such that G over M is semi-simple, then G contains a subalgebra supplementary to M in G, so this gives us that every extension of a semi-simple Lie algebra is an essential. Alright, and what's our proof of this one? We're going to let S be a Levi subalgebra of G. Its canonical image in G over M is a Levi subalgebra and thus equal to G over M. Hence, G is equal to S plus M. Then an ideal of S supplementary in S to the ideal of M intersection S is a subalgebra of G supplementary to M in G. As a corollary, and this is our last one today, it says very similar, very standard setup. Let G be a Lie algebra with a radical R, Levi subalgebra S, and ideal M. Then M is the direct sum of its radical M intersection R, and one of its, and I guess we'll call it and M intersection S, which is a Levy subalgebra of M. Proof. We know that the intersection of M and S says is the radical of M Oh, they mean R. They have, this must be M intersection R. There's a lot of typos in this book too. That's a lot to filter through of in like a video you're recording essentially live. Is it? This whole thing is dubious here. I'm going to put that there. Let H be a Levy subalgebra of M and S prime a Levy subalgebra of G containing H. Then the algebra of M intersection S prime is an ideal of S prime, and so semi-simple. Contains H, and so is H. Hence M is the sum, the direct sum of M intersection R and M intersection S prime. There exists a special automorphism of S mapping S prime onto S use a better word here. It is maps. It's not legible, but I don't have any space, so I can't really fix it. This is going to leave R and M invariant. Hence, M is the direct sum of M intersection R and M intersection S, and M intersection S is a Levy subalgebra. And so we're done. It got a bit messy here at the end. My hand is very sore, and this is long, but good news is there should be one more video of this in this series, and then we're moving on to Ato's theorem, which is going to be pretty short, and then we're actually done book 1 of Bourbaki, and we're similarly done all, that's like where all the books align, and so I'll discuss more what we're doing after that when we get there.